Hello and welcome to this video about the Baire category theorem. This is a quick overview for this proposition and how it is used in analysis and functional analysis. However, as always, first I want to thank all the nice people who support the channel on Steady via PayPal or by other means. And please don't forget, you can download the PDF version of this video with the link in the description. Okay, for start, I can already tell you the Baire category theorem is a topological claim. However, in this video here, I want to formulate it in a metric space. More precisely, what we need is a so-called complete metric space. Indeed, this formulation of the theorem with metric spaces is exactly how we need it in functional analysis. Therefore, if you want to know more about metric spaces, you can watch my functional analysis series. There we also discuss why completeness is so important. And at this point I can already tell you how you can remember this important Baire category theorem. We can simply say a countable intersection of dense sets is still dense. This is the sentence you should remember, and you should remember it holds in complete metric spaces. So maybe more formally we could write we start with dense sets. So maybe let's call them Qj. Of course, they are subsets of X, and now they should be dense. This means if you look at the closure of this set Qj, you get the whole set X. Indeed, this is exactly what dense means. A typical example would be that the complete metric space is given by the real number line R, and the dense subset could be the rational numbers Q. In other words, each point in X can be approximated by a sequence in Qj. And now if this fact holds for all j, we have the implication that it also holds for the intersection. But it should be a countable intersection, so j could run from 1 to infinity. So you see, we only have countable many sets Qj. But then, the claim of Baire is that this intersection is still a dense set. Now, after recording this part, I see I missed one important ingredient here, namely the sets Qj should also be open sets. So we definitely need to include openness here. Hence, the sentence reads, a countable intersection of dense open sets is dense again. Why we need open sets here should be clear after watching the rest of the video. So there you have it. This is one version of the Baire category theorem you definitely can remember. However, in order to state other formulations, we first need to introduce some new notions. These are topological notions, so we can formulate that in the topological space. Hence, X can be a general topological space. And usually you would say you have a set X with a topology T. If you don't know what a topology is, you can simply watch the first video in my manifold series. There I explain explicitly what a topological space is. However, of course, this is just more general, you can definitely take a metric space instead. Now, the first notion I want to describe here holds for a subset M in X. At this point, you already know what dense means, so now we introduce a new concept of nowhere dense. It's more than the opposite, because it means at no point we should find any denseness. Moreover, here I should immediately point out that all these notions are always with respect to the whole space X. So if you need to be precise, you would say the set is dense in X or nowhere dense in X. However, most of the time it's definitely clear what the surrounding space is. Okay, so now to the definition of nowhere dense. It means we look at the closure of the set M again, and now this should not be the whole space X, and indeed it should be very far off. More precisely, this means that in the closure we still don't want to find any interior points. Hence the interior here should be the empty set. So you see, the set M is not even dense in an open subset of X. Okay, there we have it. You see, nowhere dense is not really a complicated notion. However, maybe it's the next one which is definitely connected to the Baire category theorem. Indeed, this part is now about the so-called mega subsets in X. And there, I should already tell you, another popular name one uses for these sets is that these are the sets of first category in X. And there we see where the name for the theorem comes from. However, no matter which name you want to use, you should know the definition here. So, the set M is called mega or of first category if it can be written as a union. But of course, not any union. First, it should be a countable union. So as before, we could say we have J that goes from 1 to infinity. And then we have the set Sj, and all these sets are nowhere dense. So you see, since we can write M as a union of nowhere dense sets, we call the set mega. So roughly speaking, it means the set is small compared to the whole space. And then of course, we can also define the opposite of that. Therefore, then we would call the set M non-mega in X. Or, using the other language, we would say it's of second category. So you see, there are only two possibilities. Either the set is mega or it's not mega. And indeed, by using these notions for subsets of X, we can formulate our Baire category theorem. Hence, now we want to have a formulation where the name category especially occurs. Now, as before, the setup is that we have a complete metric space. Indeed, it's possible to generalize the whole thing to more topological spaces, but we will not do that now. Simply because this is the formulation that is used the most in analysis. Okay, and now the statement is that we can take any open set in X, but not the empty set. Of course, the empty set is always open, but not interesting here. Because the statement is now that an open set is always very fat. So I mean, it's not mega, it's of second category in X. In other words, a non-empty open set in X cannot be written as a countable union of nowhere dense sets. And there you should immediately see completeness is very important, because the rational numbers are a counterexample immediately. We see that because the rational numbers can be written as a countable union of single points. However, it does not work with the real numbers, which form a complete metric space. Okay, there we have it. This is also a version you can remember as the Baire category theorem. However, sometimes people only cite a very special version of this theorem. They simply say that a complete metric space implies that the metric space itself is of second category. So X itself is non-mega in X. Of course, this is just a special version from the version before, because X is an open set for sure. Nevertheless, this is a version that is good enough and indeed used a lot in applications. In fact, this is what I want to show you in the end of this video now. More precisely, in functional analysis or even in analysis, you consider the continuous functions on an interval. So maybe it's the unit interval, so we have C of 0, 1. So this is the set of the continuous functions and it becomes a metric space. So usually this is done with the supremum norm, but let's discuss the details in my functional analysis course. Here it's only important that this is a complete metric space. Okay, and now the idea is that we can split the metric space up into a countable union. And let's say that we have sets A, J here. And now inside this union, we want to collect all functions that are differentiable. So what we want is that this is a superset of the set of all the functions that are at least differentiable at one point. This means we have to define the sets Aj in the correct way to get that. Moreover, we want to define them in such a way that we get nowhere dense subsets. And everything else from our set of continuous functions we want to put into a separate set B. So you would write union with B. And now we see by the splitting here that all the functions in the set B are functions that are nowhere differentiable. So maybe we don't have all of them in there, but at least a subset. Okay, so this is the overall idea, to show that we have functions that are nowhere differentiable. Indeed, now you can believe me, it's possible to do this, so we are able to define the sets Aj. Hence, we simply can apply our Baire category theorem, which tells us that the whole space here is of second category. So we see this here is a meager set, so B cannot be a meager set. Most importantly, B is not empty, so we have functions that are nowhere differentiable. However, we know even more, most functions we have lie in our set B. So these functions that are nowhere differentiable but still continuous form a non-meager set. Indeed, in a complete metric space, now it's possible to show that non-meager means that the set B is dense in the continuous functions. So in summary, we can say by using the Baire category theorem, we can show the existence of functions that are nowhere differentiable. So we don't have to construct these functions at all to see that they form a very important part inside the set of the continuous functions. Indeed, this is an approach you can use in other contexts as well, where you want to show the existence of some elements with some special properties. The idea is just to shift the complement properties into such a meager set. And then you can use the fact that the whole complete metric space should not be meager. Okay, and this concludes this overview I wanted to give you about the Baire category theorem. And please don't forget, you can download the PDF version of this video with the link in the description. And with that, I hope that I see you in the next video. Have a nice day and bye!